Today we're going to be talking about solving systems of equations by substitution. Substitution and graphing are different methods to do the same thing, which is solve a system of equations. Now there are actually three methods that we use to solving systems. There's graphing, substitution, elimination, and when you're solving a system, it's kind of best to use which one works best for you. What are you most comfortable with? What's easiest in your mind? Certain things, there are certain clues that you want to look for that are also helpful when deciding which ones. For example, if you see both in slope-intercept form, sometimes it's easier to use graphing. If you see one in slope-intercept form and the other equation not, then sometimes it's best to use substitution. And lastly, if you kind of see both in the standard form, then doing elimination is kind of the best method. Now again, that's just a good idea to use, but it really comes down to what you are most comfortable with and what you can do well. So let's try to work on solving some systems by substitution. Now, do keep in mind, when we solve a system by substitution, we're going to have similar solutions. For example, one solution, no solution, infinitely many solutions. So we'll look through those and we'll kind of talk about each as we come across them in the lesson today. So here we have a system of equations and they want us to solve by substitution. So I noticed that both of them are solved for y. So being that one of the equations is solved for something, we can take that and plug it into the other equation. That's what it means to substitute. So normally when solving by substitution, the goal is to get at least one of the equations solved for either the x or the y. It really doesn't matter, but whatever's easiest. Now in this case, they are both solved for y. So what I am going to do is I am going to take what y is in the first equation, and I am going to substitute it in for y into the second equation. So we're taking the second equation, and we are going to replace that y with what y is equal to in the other equation. So we have negative 4x plus 20 is going to be equal to x minus 5. So we substituted in that equation, what y was equal to, into the other equation for y. When doing so, you now create an equation where you have just one variable, okay, the variable x. And so this is where we use our inverse operations and combining like terms and distributive properties to make sure we can simplify and actually solve for the value of x. So what I like to do first is I like to get the x's on the same side. I just prefer to have less variables all around, so I try to simplify those first. So I get negative 5x plus 20 is equal to a negative 5. Then I continue using my inverse operations. I see that I have this plus 20 that I can subtract to the other side, and I get negative 5x is equal to negative 25. And lastly, dividing by negative 5 to each side, giving me x is equal to 5. Now, do remember that when we graphed, we either got a solution, right? When it was one solution, there was an actual point. Okay, it had an x and a y value. Every single point has an x and a y value. And so when we solve for x, we're not actually done. Okay, we're not done because we only have the x value and we need to actually have a y value as well. We need to actually have the actual point. Remember, if we were to graph this, we're hoping that those two would intersect at a particular point. And so that's kind of what we're finding through algebra. So we're going to take what we have and we're going to plug it into either equation. It doesn't matter which one. You find one that looks easier to you. In this example, I think for me, y equals x minus 5 is going to be the easier equation to use. So what I am going to do is I'm going to take what x is and I'm going to substitute it in to the x into that equation. So I get y is equal to 5, that's what we're substituting in, minus 5, and so we simplify. Well, 5 minus 5 is 0, and now I have found both the x and the y. So the actual and final solution to this system is the point 5, 0. Now again, if I were graphing this, I would see that these two graphs intersect or cross right at that point 5, 0. But instead of graphing it, we did it algebraically. We worked it out and we found the point. And again, remember, you're always trying to find both the x and the y value. Okay, you can't just have one or the other, you need the complete point. So here's another one. I would suggest you give it a try on your own. After working through it, hopefully you got the point. 1, 5. Now, as you work through it, do remember, if you didn't get this answer, what you need to do is you need to go back through your work. Look to see, did I plug in to the correct variable? Okay, did I do the inverse operations and combining like terms and distributing correctly? Looking to make sure you have the right signs for everything. So if you did not get this answer, please go back, double check your work. That is one of the biggest things that we try to do in mathematics is we have to go back and look through to look for our errors, fix those errors to work through. Because one difficult thing about solving systems is if you get the first part wrong, you're going to get the rest of it wrong, right? But that's not the main issue. The main issue is just making sure you learn to go back and go through and search through any of the errors that you possibly have. So here's another example to solve by substitution. Now in this particular example, it's slightly different than the last two. The last two we had y was equal to, and both equations were in a sense in slope-intercept form. Now here, notice that only one of the equations is slope-intercept form. Only one of those equations is solved for something. Now that's okay because that's what we need. We need at least one of the equations solved for something so that we can then take that and substitute it into the other equation. So because this one is solved for y already, I am going to take what y is and I am going to substitute that in for y in the other equation. So I'm taking the first equation, 5x minus 2 times y, which is going to be equal to 2. We're taking that first equation and we are replacing the y. So I get 5x minus 2. Now instead of the y, I'm going to plug in what y was equal to from the other equation, which was 5x plus 4, and that's all going to be equal to 2. So then I go ahead and simplify by doing my distributive property, combining like terms and inverse operations. So I start by distributing. I get 5x, and then negative 2 times 5x is a negative 10x. Negative 2 times 4 is a negative 8. And that's all going to be equal to 2. Then I look and see that there's some combining of like terms that I can do. 5x minus 10x is a negative 5x. Once I've combined like terms, now I can start to do those inverse operations, getting the 8 to the other side using my inverse operations, and then getting that negative 5 to the other side. So we end up getting x is equal to negative 2. Now again, we're not fully done. We only have the x value of our solution. We need to find the y value as well. So what I'm going to do is I'm going to go back to either of the equations and use that to plug in what value I just got. Now, I do notice that this one's already solved for y, so that might be the easier one to use. So I'm going to take the equation y equals 5x plus 4, and I am going to replace my value, the x value that I got, into the x value here. So I get y is equal to 5 times negative 2 plus 4. Do some calculations and simplify, and we get the y value. So now we have the complete point, the x and the y. Thus, the solution to our system is negative 2, negative 6. Okay? This is the one solution. Again, if we were to graph these, we would see that they cross at the point negative 2, negative 6. All right, so let's go ahead and again try to take a minute to work this one out on your own. After you've worked it out, hopefully you ended up getting the answer 0, negative 2. Again, if you didn't get that answer, go back and see, where did I mess up? Okay, did I forget a sign somewhere? Did I do the wrong inverse operation? Did I not combine terms correctly? Did I not distribute correctly? Okay, are there any missing signs? So remember, whenever working it out, if you're not getting the exact same thing, double check your work. That's one of the key things that we have to do in mathematics, is always double check our work. Now for this particular system, notice how neither of them is solved for something. Okay, it's not solved for x, it's not solved for y. So what you have to do in this particular situation is you have to figure out which equation you think would work better for you and which variable do you want to solve for. And so sometimes that's a little tough thing to do, right? Because you have to think about the process. You have to actually think about the steps before you actually do them. You're thinking through, if I took this one and solved for x, what would I be doing? What would that answer look like ahead, right? So that's the hardest part about these ones, is trying to figure out which equation you should use and which variable you should solve for. Now, once you practice this more and more, you end up getting the hang of it. So what I noticed for me is I kind of like this bottom equation. I know that no matter what, if I divide everything by 3, it's all going to come out nice and pretty simple. So I'm going to take this first equation, the second equation, and I am going to solve it for a variable. Now, which variable? It doesn't really matter. You know, since we've had some practice before about solving things in slope-intercept form, maybe I just solve for y, because I've had practice with that. So I'm going to go ahead and kind of get it in slope-intercept form, because that's kind of how the other ones work. So I'll do my inverse operations and simplify. And now I have written an equation in slope-intercept form. Basically, I have solved for one of the variables. Now, obviously, we don't have a number answer here, but if we looked at the previous examples, at least one of our equations looked like this. So now that I have this, I can use this to substitute in to the other equation. Now, because I worked with the second equation, when I take this particular thing, I do need to make sure I plug it in for the y value in the other equation, not the one that I used. So I'm going to take the 4x minus 2y is equal to 2, and I am going to plug in what I just got for y. And so I get 4x minus 2 times negative x plus 8 is all going to be equal to 2. Now again, I've created this situation where I only have one variable, so now I can do some simplifying distributive property first. 4x, negative 2 times negative x is a positive 2x. Negative 2 times a positive 8 is a negative 16. is all going to be equal to 2. So I did the distributive property first. I notice I have some like terms here, so I'll go ahead and combine those. And then I'll finish up by doing the inverse operations and getting x all by itself. Now we have the value of x, but remember, we always need two things. We need the x and the y. So being that I have the x, there's a couple of things I could do. One, I could take this and plug it into either equation and then solve for y. Now, I do notice I already did some work. I got y kind of already by itself. So actually, being that I got y all by itself, I might as well actually use my more simplified equation. So I'm actually going to use this one. I'm going to take the y equals negative x plus 8, and I am going to replace or substitute my value in for x. So I get y is equal to negative 3 plus 8, and then do my simplifying. So I get 5 here, and now I have my complete point, 3, 5. So again, if I were to graph this, these two would intersect at the point 3, 5. Now again, there are so many different ways we could have started this. We could have took the first equation, solved for x. It would have been a little bit difficult because there would have been some fractions there, but it would have been fine. You could have taken the first equation and solved for y. You could have taken the second equation and solved for x. So there are so many different ways that you could have done this. But remember, the end goal is making sure you're just doing the correct work, plugging in correctly, solving for one of those variables, and then plugging in to get the other one. So let's go ahead and try one of those on our own. So take a minute, see if you can work through that. After working through that, again, hopefully you ended up with the point negative 8, 7. Again, I know this was a more complicated one, but look through, double check your work. If you didn't get the right answer, look to see where you messed up, what you did wrong. Look for signs that were off. Look if you forgot to distribute correctly. So kind of notice those things. It's good to kind of notice your errors and be able to fix them. So that way you can always see where you went wrong to get the right answer. Now again, one thing I haven't noted, which I'll note now, is there is also a way that you could always double check your answers. I didn't do it with any of the problems, but what you could do is you could take your x value and plug it in, and you could take your y value and plug it in to the exact same equation, and when you simplify that equation, if it makes the equation true, then perfect. But you have to do that with both of them. So then I take the same x, plug in the y, I simplify this one. If it makes both of these equations true, then I know it is the correct answer to the system. Okay, but again, if you take that point, you have to plug it into both of the equations and check both of the equations, because if you don't, if it only works for one and not the other, then actually you don't have the system or the solution to the system. So be very careful of that. Okay, you may have a point that's actually on this graph, but not on this graph, right? And we, looking for systems, when we're solving systems, are looking for the one that actually is on both of them, where they both intersect and cross. All right, we're going to do one last example. So again, I'm given my system. I note that, one of them is solved for something, so that makes it a little bit nicer. So I'm going to take what it's solved for, and I'm going to plug it into the other equation. So I'm going to take that 7x minus y, and I'm going to plug it in, the 7x minus 1 in for y into that equation. So I take 7x minus 7x minus 1, because that's what we're substituting in for y. I notice that I have a minus sign in front, so I do need to distribute that into the parentheses. So I get 7x minus 7x plus 1 is equal to 1. Now in this case, I do need to combine like terms, but something happens. 7x minus 7x is 0. That means the x's go away. These, in a sense, cancel each other out. So I have no more x. Really, all I'm left with is 1 is equal to 1 because these guys cancel each other out. So what am I to do now? This is one of those special cases. So there will be times where your variable gets canceled out. And what we look for then, if that's that case, is this final part. We look at the final part and we have to notice either one of two things. One, it's going to be equal and true, which it is in this case, or it's not. Well, in the case that they are equal and true, 1 is equal to 1. This is actually the solution of infinitely many solutions. This means that these two are actually the exact same line. Okay, if you rearrange this, you would have saw it actually would have came out to y equals 7x minus 1. They are the exact same equations. So in this case, that means that every single point is a solution. That's why it's infinitely many solutions. If we were to have graphed this, we would see it's the same exact graph. One right on top of the other. And so that is why it's infinitely many solutions in this particular case. Now again, to make a side note, do remember if we did something like this and the variables disappeared, they canceled out, but we ended up with something that wasn't true. So example, let's say at the very end, instead of 1 equals 1, let's say it said 2 equals negative 5. Well, this is definitely not true. And if this situation happens when one of your variables disappears and when you have none left, then this would be no solution. Okay, this is that idea that it would be that parallel lines, that the two equations are parallel, they'll never cross. So algebraically, it'll look a little bit more like this, that the variables will disappear, but in the end, it won't be true, right? And so that's that. If it's not true at the end, then it's no solution. But if it is true, like it is in this particular case, then our answer is infinitely many solutions. Okay? So those are the special cases. Do look out for them. It does happen. Again, you'll notice that sometimes the variables will cancel out. And if that is the case, you're just checking the very end and then figuring out if it's one of these two. And if not, as you saw with all the other previous examples, then you're going to have one solution, which always has one x and one y. I hope this was helpful, and good luck on trying this on your own.